Okay, so today I'm going to go over the quiz chapter 3 for you guys. So the first question has multiple parts. We're labeling the acids and the bases. We need to say if they're Bronsted, Lowry, Lewis, or both, and then we need to label the conjugate acid and bases. Finally, we're labeling the nucleophile and electrophile, if there is any. So when I'm looking for acids and bases, I usually start with Bronsted, Lowry, because if there's a proton, then it's a lot more obvious. There is a proton right here. And it seems like if we're going from this structure in the before, in the reactants, to this structure in the products, it does lose that proton. So I'm going to say this is an acid. And because it's proton-based, it's a Bronsted-Lowry acid, but it's also a Lewis acid because as it loses the proton, it accepts the electron that's left behind. So it's both. And then if this is the acid, this is going to be its conjugate base. So if this is the acid, then the other thing must be the base. And it does accept a proton. It goes from NH2 to NH3, so it's gained a proton. And it also, that means it's Bronsted-Lowry, but it also is using this lone pair to create the bond. So in that way, it donates an electron. So it's also a Lewis base. So this must be our conjugate acid. So that's how I would start with that problem, is I would look for a Lewis acid or a Bronsted-Lowry acid or base. And then I would think, is there also electrons changing hands for the Lewis? And we've labeled the conjugate base and conjugate acid based on what the acid and the base were. And then for nucleophile and electrophile, a nucleophile has excess electrons. It's looking to give them away. So technically, this here can act as a nucleophile. It's attacking this proton. And the electrophile is what's being acted on. So this would be an electrophile. So that's how I would approach that question. For question 2, ranking the acidity. Now, normally if we're ranking the acidity, my first instinct is to check the pKa. But in this kind of question, all of these are the same group, so they would technically be really similar pKa's, right? They would all be in the 16 to 18 range. So then I have to say, is there anything else that makes these different from one another? Well, the only thing I see is these have really inductive groups on them, and this one doesn't. So this doesn't have an inductive group on it. Every other one does. So I'm going to say this is the least acidic. This is the weakest acid. It wants to give this up the least because the electrons will be really concentrated here. And that is something that I've talked about in some previous videos and in class, is when I think about acids and bases, I think about how well can it handle the electron pair that's left behind when the proton is given up. So in this case, the electron pair is going to be really concentrated here. But if you go over to this with 6 fluorines on it, these fluorines are all really electronegative. So they're really comfortable taking any of the electrons that are left behind, and they'll have the inductive effect. So these electrons that are left on this oxygen are going to be pulled away. So the effect of these fluorines is going to make this much more acidic. This has 6 fluorines and this has 3. And this has 3. So between these 3, I think this is the most acidic. So now we're left with these two. They both have 3 fluorines, but this fluorine is one away from the oxygen, and this fluorine is 2 away. So the closer the electronegative atom, the more easily it can pull electron towards itself. So that's how I'm going to come up with my final answers. Okay, next question. Identify the most acidic protons. So I'm going to again think about my pKa here. The pKa of an amine is usually 38. Put a little about 38 there. And the pKa of an sp3 hybridized is usually about 50. Now there is some inductive effect going on here, and this has a resonance structure where there's a partial positive, so it would probably be a little bit more acidic than 50, but it's going to be in the 50 range, and this is also probably going to be a little more acidic than 38, but it'll be in the 38 range. So because of that, we can say that these are going to be more acidic. The other thing this has going on is there's a resonance structure. So if one of these protons is lost, if we have a base come and take a proton, you'd end up with this nitrogen that has 2 lone pairs and a hydrogen. Well, there is a resonance structure where this can go like this after it's lost a proton, be O minus and nitrogen here that's slightly positive. So that is also something else a nitrogen can do. If you had a lone pair left behind, it could do something similar, but it's not going to be as stable as in this form. It's going to be more acidic. Okay, and then for question 4, predict the product of the acid-base reaction in the box, then indicate which side of the reaction is favored, left or right, by circling the favored side. Show the mechanism and justify your answer. So let's start with predicting the products. Well, which one of these is going to be my acid and base? This is already negative, so it has an extra electron to give, and this has a hydrogen available. So I'm going to say that most likely this would be my base, and this would be my acid. So if this is the acid, it's going to lose a proton. If it's Bronsted-Lowry acid, which because it has a proton available, it is, and becomes negative. And this will gain a proton to become positive. I usually don't predict the reactions, the products of the reaction first. Usually I would draw the arrow. This is trying to get a proton wherever it can, and then that would break, leaving the lone pair behind here. So that's the curved arrows. So we predicted the products, we showed the mechanism, we need to indicate which side is favored. So the way I'm going to indicate which side is favored, I'm going to compare the acid and the conjugate acid. This acid would have the conjugate base. So you can just compare those pKa's. The pKa of this of sp3 hybridized hydrogens is about 50. It's not very acidic. And the pKa of this is, this is a great opportunity for me to talk about resonance. You might not know the pKa of this structure right off the top of your head. Because it's CH3, you might just say, oh, it probably is also close to 50. But because you have this resin effect, this is going to be less than 50, so more acidic. Where you've seen something similar is if you have a phenol and then you have a phenol and an alcohol. This phenol is closer to 9, while this is still in the 16 to 18 range. So that's because when the proton is left, the electrons left behind are going to be distributed around the ring. So I'm going to say this pKa is less than 50 because the same thing would happen. If this loses a proton, the negative charge would be distributed around the ring. So because of resonance. So I'm going to say this has the weaker acid and the weaker base, so it's favored. And a friend of mine said low to high, it will fly. So if you have a lower pKa to a higher pKa, or a smaller to a bigger pKa, it will proceed that direction. If it's high to low, it won't go. So this direction, we have a bigger pKa to a smaller, higher to smaller, so high to low, it won't go. And I think that this pKa is smaller due to resonance. And then I think we've done all parts of this. We predicted the products, we indicated which side was favored, we showed the mechanism, and we justified our answer. Okay, finally, this question states that acetamide is typically protonated here on the oxygen, not at the amine, which is surprising because usually an amine is a better base than a ketone. However, in this case, that's not true. The reason I think that's not true is because there is a resonance structure where oxygen is negative and this amine, NH2, can donate its electron pair to fill in NH2+. So because of that, there's already a partial positive in this nitrogen, so it doesn't want to gain any more positive charge. And there's a partial negative on this oxygen, so it's fine with gaining a little bit more partial charge. So due to that resonance structure, actually, the protonated form would be this. Okay. I mean, technically, I guess you could have OH and the NH2+, but it'd have a resonance structure with this. Okay, well, I hope that was helpful for you guys for the Chapter 3 quiz. If you have any questions about acids or bases, please feel free to reach out to me.